facilitates the secret communications better than the existing one. So, and I purposefully avoid the topic of post-quantum because there is no such definitions exist of post-quantum, but it comes in the area of quantum cryptography and PQC concepts as well. So, if you look at the mechanisms where earlier days used, it starts from the wooden writings and from X-bit and earlier then it becomes papers and used different mechanical materials and machines to use secret communications. Basically, these are like machines or some form of information containers which used to conceal the information. Then slowly it moved, as I said, the computer entered in the information era, then it moves to a modern cryptography. Right? So Sanan, very well, he defined information theory in a different sense in a computer terms. It's more logically he defined information in a different senses, right? So he used the information theory using entropy, how to design a communication channel between a sender and receiver with probably some errors. And he designed a very nice model. Till date, we are using the same model for transferring the information from one end to another end. So he also introduced a concept of modern crypto. He's a beginner of modern cryptography, and he started working on the one-time pads, where just pad the information along with another key so that it becomes more secure. Still, that one-time pad is a hard problem; it cannot be solved, right? And there are some issues from one-time pad since the key size is very long. So it's very difficult to share these keys. And then followed by there are many public key crypto systems arrived where a public-private key that it is a better mechanism of delivering keys. And there are some hard problems are introduced like discrete logarithm, integer factorization, prime factorization problems. And then people in end of 19th century moved to pretty good privacy where it delivers end-to-end security. And very well, these are algorithms like advanced encryption standards and data encryption. These are like standards already been defined, and we are working on the proper crypto systems delivering end-to-end secrecy. But if you look at the current crypto architecture, it has various levels of layers. Starts from the application level security and then network level security and then hardware level security. Middle, there are so many level of security layers. Another thing is, if you look at the contemporary crypto algorithms are based on the solid information modeling, and it's based on the math, right? So it's basically a math model, a logical idea where information is represented as logical bits, and then logical bits are used to perform a different operations. That's basically a transformation, right? So, and then the mid of 19th century, there was a debate whether information is physical or information is logical. Okay. So there is a paper in 1991 during after that the conference where Richard Feynman also was part of it, and this guy Love presented information is physical. That's the beginning of quantum. So I think right any systems, like whatever informations we dealt with so far, because we have a computer, we deal with only a logical senses, right? It's converted into bits, zeros and ones, and then all the crypto algorithms applies on that bits in a logical level. But we never bother about the physicality of the information, right? So all the informations are stored somewhere in a physical object. That's what he trying to demonstrate. Information is no longer is a logical phenomena. It is basically a physical phenomena because it has some physical storage, and you have to fundamentally you process from the physical notions. That's the beginning of quantum, where if you understand all in the logical level, then you need a level of security layers. You have to protect in the hardware level and the network level and the application level. But what he proposing is, it's something is as a bare metal level. So information is physics, and it is stored in some of the physical objects. So with this, it ends up with the research in the logical level, and it elaborates the degree of freedom how it works in the physical world. Now, whatever we have algorithms we have in the physical logical world, how is it truly unbreakable? Okay. So, because it is, as I said, it's a formation of mathematics and information theory, and Shannon's proved that one-time pad is truly unbreakable. Still, it holds the true, and even quantum computer comes. And the key is the only secret. As per the Cryptography principle, the key is the only secret, which can be used for and reused for a different padding. Right? But the only drawback this OTP has is serious drawback is key transfer, because if the information, the message is too long, then you have to increase the secret bit size as well. So it is equal to a message length. Then it is very well known in the crypto areas, where the the sharing that such a big key is equal to sharing your message. It is again a headache for us to deal with. So that's where all these things comes. So the challenge is, as you assume, if this information is logic, then all these computational problems is coming in, and you cannot achieve unconditional security. So there is some limitation you need to set for attackers. Then only you can achieve these kind of securities. Now, but this is an open world. Everybody has freedom, and attacker has freedom. So we cannot restrict anything for attacker access. That's the challenge current nowadays. We are focusing the day to day. The attacks are increasing because of we are underestimating the attackers. So I think I have 2-3 slides on quantum computing. Hopefully there was a nice explanations in the last couple of lectures how this qubits works on that. So just the history, it started from Feynman, Richard Feynman is a Nobel Prize scientist, and he started concept of using quantum simulation designing a computing machines, right? So how quantums, the atom can used to design a computing machine. He just started the idea of simulation, and then followed by 1980s, it is an ideology becomes a universal, designing a universal quantum computer. Now, if you look at the current trend, everybody started, IBM, Google, everybody started working on these designing a quantum computers. So it has a significant growth in this current century and the current years. So the advantage of the quantum is a superposition principle, where it is acting as a multi-state, it's a superposition state. So simple is analog of classical with the direct bit notations, how these classical bits can represent as a qubit. So the qubit is nothing but a photon which has some properties. So if you look at the diagram here, it explains nice how the qubit graphical representation is. So where is the empty box in the Left hand side represents there is no value. It is 0 directed, and the box with complete side of hello, it represents 1. It's full, and the mixer of these both state is a superposition state, where one block is enough to represent 2-bit of information. That's the fundamental of qubit, right? So this qubit has some inherent property where it acts as a 0 and acts as a 1 simultaneously, because it evolves some nature property. Basically a photon, a quantum of energy. So it's quantum of light energy, which exhibits the behavior of different two different states simultaneously. So the application of this quantum theory is one is Grover's algorithm, where I think Dr. Prem explained that how this Grover's algorithms work, and how it made it unstructured search easy, very easy, and factorization problems. So the source algorithms, how the factorization is easy, which source algorithms. These are inherent. These two scientists used inherent property of quantumness and make it a simplified version of the hot problems. Okay, so now the main application of quantum communication is quantum cryptography, and you know the quantum cryptography uses the quantum mechanical properties to perform a cryptographic task. Now, and also it promises, as per the laws of physics, it is unconditionally secure, and also it is very fast, ultra fast, because it's all light energies travels equivalent to a light, so the computation becomes ultra fast. Now, so why the quantum mechanical properties being used? If you remember in the couple of slides back, I discussed whether information is physical or logical. So there nowhere, if you see in our information theory, mechanical properties be not been used. But in a quantum information theory, the mechanics is playing an important role, because all the phenomena that we study as a photon or a qubit, it is a physical entity. It is a physical entity. It has a property of behaving like it has a spin or it has a rotation. It has multiple states, mechanical states. So that's where the quantum mechanical properties being used to pick these states and make it encoding and decoding happens. So the fundamental idea I'm trying to enforce is all our objects are physical objects. It is now no more logical world where you just only write an algorithm to process, because we work on the physical world where everything exhibits a mechanical property and then follows a mechanical structure, right? So all information, zeros and ones, are use these balls, mechanical balls, which is nothing but a quantum, for encoding and decoding. And also it has another property. If someone tried to read this information, and the state of this quantum, the photons, the balls states collapses, because it has a property of wave particle duality. The photons arises, sometimes behaves as a wave and sometimes behaves as a particle. So that's called a wave dual particle property, which is completely unpredictable and uncertain. Once if you measured and observe that, and then it completely collapses. It's basically consuming energy, right? So if you consume the energy and utilize it, then it transforms to another form of energy. You cannot retain back those kind of energy, because it's basically energy packet. And so it is easy to identify the eavesdropper in the quantum channel, because these quantum bits are prone to measure or identify. So before I move to there, and you might have heard that yesterday, the word messer, right? Think I'm a bit hesitant to ask questions to professors, but still. So why do you think the messer is used in our this quantum senses, right? It's a computing or communication. People you frequently use the term called measure the photon, right? But you never been into the classical bits. We never use the word in classical information theory measure. It's maybe just count the bit rates and count. It's all countabilities. Now we are using measuring. So I think anybody is invited to answer.
Yes, sir, because in quantum like in quantum communication, qubits are existing in simultaneously in multiple states with different probabilities. So only if we measure, we can bring it down to a typical state which is having the highest probability. So possibly that's a reason.
Yeah, it's a good attempt. Yeah, so probability, I understand. Yeah, so probability is a measure, but the only thing is a little more
Yeah,
deeper. It's a number, but I'm just thinking of probability. It's quantity, but
since it's coexisting in multiple states simultaneously, to bring it down to a single valid value, maybe.
yeah. So state is again discrete.
Yeah.
So discrete phenomena can be countable, right? So why do you use any other guess, please? Okay. So I'm not going to force anybody. Okay, so the reason is there are two systems you see. One is continuous functions and discrete functions. So discrete functions, all your classical bits, zeros and ones, are discrete phenomena where you can count 1, 2, 3, 4, 5. It's countable, right? But in a quantum, all qubits are continuous in the sense, as I mentioned, it has a property of wave particle duality. It behaves as a continuous function. It is not just a one bit like
somebody unmuted the mic, sir.
yeah, sure. Okay, so the idea is here all the qubits, it is for representation, it looks like a discrete phenomena, but in general, it is a wave. It's a light particle. It is basically a wave which represents a qubits, right? This wave is a continuous phenomena. That's where people use a term called measure, right? It is, since it's a continuous phenomena, like your height or like your weight, it's in that you cannot measure it in precisely. That's why called as measure your weight and measure your weight, right? So likewise, this is also a continuous phenomena. That's where people use measure. So measuring the qubit, right? So, and this is there are some set of special equipments is required to produce these qubits using this light, and then capturing it in the other end using some thing called detectors, which is the photoelectric avalanche effect materials. But in general, people used to call is a measuring qubits because of it. Okay, let's not spend much time. Good. So overall, if you look at the mind map of quantum cryptography, it has a lot of dimension, if you see. But I'm going to touch only a few things in that. But for you to understand this broader area, here is first is a quantum key distribution systems (QKD), and it has many branches. It starts from a QRNG, quantum random number generators, and different protocols and different categories of implementations. And there is a concept called repeater, because so far quantum memory, the storing a quantum state is not at all possible, right? Another important thing I just want to stress here is In some of my previous talks, people used to ask, do you need a quantum computer to do a quantum cryptography? Definitely not, right? That's so because you don't need a quantum computer to execute this. It basically small devices like a basic lasers and some of these special purpose detectors and some of optical materials is enough to execute this quantum cryptography, right? So that's where the quantum key distribution is. Already there are many commercial systems available. Another important area is quantum signatures, digital signatures. I think Prem has explained that. So there are many quantum signatures is coming in, and it is used for various purpose like generating signatures or that. And quantum money is another important area where it proposed way beyond than BB84, where you just detect the counterfeit currencies using qubits. And some of the device independent. Another beauty is irrespective of sender and receiver here, no one can decide key because this key is generated dynamically. So that's where the device independent systems are coming in. Device can be produced by even a hacker, but still we can create a trusted key. And secure two-party communications, it's like beyond the QKD protocols, what else we can do? Like something bit commitment and oblivious transfer and secure secret sharing, multi-party communication. These are the other possibilities where you can do the quantum crypto. Right. Now we'll come to, I think this talk only focus on the QKD, quantum key distributions and advances in quantum key distributions and what the current scenario in Q. Right. So as I said, QKD provides unconditional security. So the unconditional security means the attacker is open to see any of the systems we have, right? Still we can generate key. If you look at the diagram up, there's a center and receiver. The key is encoded as a qubits or single photons and send it to a receiver capturing it, and then is translating it a key, right? It's happening in the quantum channel, and we need a classical channel to perform some other post-processing activities. So beauty of this quantum channel is if some intruder or attacker trying to measure this qubit, the state of the qubit is completely collapsed. Sorry. So end of that, it results wrong key in the both end. So we'll discard that transaction and start a new transaction. It's very simple that it is very hard to copy the quantum bits, and it is very hard to measure this without leaving the traces. These are two fundamental properties of quantum channel. I'll explain relate with the physics and principles why it is behaving like that. Sorry. So here is QKD systems is possibly secure. How can what are the facts that this QKD system is secure? One is sender and receiver must be easily exchange the keys in front of Eve, right? Because Eve interventions can be easily directed by the sender and receiver, right? According to the laws of physics. And device independent security. So here is two devices we believing that it is legitimate, and either sender or receiver cannot decide preset keys, right? This key is generated online, right? So no one can decide key, because the key will know that end of the transaction only both the sender and receiver parties will know what is the keys, because it's completely dynamic. It is no bias. So the key is generated on fly, and this closed nature of QKD systems, because it is a controlled environment by light, and it provides a high ultra-scale security, unconditionally secure, and the protocol is executed in trusted environment as well. Right. So since these QKD systems are closed in nature, the quantum channel is very sensitive. It adds another value add for this QKD security and secure against the collective attacks. So all other existing attacks can be neglected according to the theoretical descriptions. Still, we are facing some challenges in the practical implementations, but most of the attacks can be avoided using these QKD systems. Right? So these are like a major factors where how QKD systems are secure. Right? I think I have 4 slides for quantum mechanics, which is related to security. Right? So I think the quantum mechanical part is one is select preparation of quantum bits and qubits and encoding with classical information and measuring it. For measuring this qubit, that's for a center end and the receiver end, we use some kind of filter. This is again a physical filter, and just for a logical representation, I made it like if you look at the yellow one is a basis horizontal vertical filters, and there was another one is diagonal anti-diagonal filters. So these two filters are used to measure the photons. So photons are measured according to its orientation, where these photons can take up spin or down spin or vertical spin or horizontal spin or a diagonal anti-diagonal. So based on that spin, the information is encoded in that particular photon, and then photon is measured using these kind of basis choices made by user. So the measurement is happening like this. If you look at the measurement title under that, so if a horizontal photon goes into the basis choice of horizontal vertical HV yellow mark, where it takes the yellow mark and it takes the horizontal vertical polarized basis, and then it passes through, right? Then it yields the complete value at 100% probability. Whereas if the same photon passes through this basis, it may not receive complete in other end. So there is a 50% chance can be predicted as a anti-diagonal and 50% chance to predict a diagonal. This is, I think, very well explained by the DRDO scientist, I think, the other day. So this is basically how this measurement works. Right? So according to the basis choice, the information can be decided. So the users or receivers have a freedom to choose this basis. He can take any basis of his own choice, freedom, and then he can measure any photon. And also receive center can produce any photon with any type of orientations randomly and then send it. Once this transaction done, then finally we will derive the key. Right? For that we need quantum gates and some of the transformations. So these are transformations used to manipulate these qubits according to the operations, and then produces the final qubit operators. So basically this is a vector space, and special case is it is a Hilbert space. All these qubits obeys the properties of Hilbert space. So, and it is run on the field of complex. We use operations or unitary operations, and some of this tensor product. Okay, let's discuss only 2 important properties of quantum mechanics, which is heavily used in quantum cryptography. One is no cloning theorem. Think from the name itself, it displays the copying is completely denied. So any qubit with any different operations, you cannot copy that qubit, exact qubit, or otherwise in physics, you cannot make the same energized packet, quantum packets. Okay. So let's understand with a simple example. For example, we have a one apple, but we want to give it to two kids. It's impossible because the two kids, the kids wants the same apple, right? So in general, in practical, there is no system or physical process exists to create a same apple, right? Because the same apple, when I say same color, same weight, same the structure, everything ditto. Even if you go the tree which produce the same apple, you cannot identify the identical object, right? Because the reason is very simple. It is produced by nature. So all the objects which is produced by nature are unique. It's a fundamental of quantum mechanics is all objects which is produced by nature is unique. You cannot create or clone a copy of, including if you see human beings or whatever plants, what trees. So you cannot create a copy of that. Similarly, photon is a light energized particle which is produced by a quantum source, nature source. So the demonstrated experiment is state that you cannot create a copy of a qubit or you cannot clone a copy of. So that's where if you see some of the things, it is called as linear optics, where it is allowed to use one single qubit. You cannot go for operation like multiplication x squared operations, right? So the copying is not allowed because it's a non-linear operations. So we all talk about linear quantum optics. Another important property is uncertainty principle, Heisenberg uncertainty principle. It's simple principle. It is stated that position and momentum of a quantum particle cannot be determined, right? So the position and momentum is, it's a simple equation like position times and momentum is greater than or equal to the Planck constant divided by 2. So this a funny example. A physics scientist, he he wants to go a party outing with his friends, and he took his quantum car and started driving to somewhere at Goa, right? But his wife is a mathematician. He just she somehow identified he's going for some outing. So she just want to catch her. So what she did is trying to bring her his phone, the scientist phone, and trying to inquire where he is. Then he just tell the location. And then he asked for what speed you are driving. So then he just see the speedometer and inform the speed at which he drives. So with that, the mathematician trying to compute the location expected to arrive and trying to catch him. But unfortunately, she couldn't do that. Then again, she made a second attempt asking the location and the speed at which he drives and trying to catch him once again. And then second time also. The reason is he's driving a quantum car where you cannot predict or you cannot measure precisely location and momentum, right? So just a kind of a funny example people physicists used to tell. It is hard to predict momentum and position of a qubit simultaneously. So this is another important behavior which is used. Even they are trying to predict this qubits orientation. It is impossible to predict. So nobody can have. So it is another important uncertainty principle which is used for in quantum cryptography. Right. Now we move into key distribution problem. Right. Since we are interested in applications, so I thought of going into a very specific problem as a key distribution problem. So this is a first problem where first applications identified in the quantum world. Before the computing in the quantum communication world, key distribution is a first. Someone may ask a question, why don't you send entire information to in a quantum channel? Why only key? The reason is very simple. If we have a sophisticated quantum channel and without a loss, we can send information, no doubt about it. But extract the entire information because of heavy losses in the quantum channel, and it is prone to make noises. So we try to get key out of it, secure key. Then we can use our traditional encryption algorithms to encrypt and decrypt and send it to a classical channel. So this is used some of the special case, at least as an initial step. Maybe a step forward or 2050 or I'm not sure, where we can use the entire quantum channel for our communications. Okay. So as I explained in many slides, this class, it is completely different from a classical cryptography because it is it deals with all physical objects and it guaranteed that unconditional secure. And also it is providing an additional monitoring feature where you can monitor the entire channel. So it is under the control of sender and receiver's knowledge where they can monitor their private channels. So for example, if you see fundamental information materials like paper documents, other secret letters, our USB stick, our magnetic tabs, and our radio signals, everything can be tapped and people can read your information without your knowledge, even without any leaving any traces, right? Some secret letters, if I read and give it to someone, he may not be able to notice that it's read by how many people. Similarly, your USB stick, everything, our communication channel can be tapped by anybody. So this is something is a question of privatization of these things. So that's where we move on to the quantum, where you can design a complete private system. If someone intruder comes in, we can definitely catch him. So as a result, it offers a fundamentally different solution to solve this key distribution problem. And it is also a solution for sharing a secret string between two parties. And at this point of time, it's offering a symmetric key solutions. Right. Now, what are the fundamental principles of quantum key distribution systems? Right. So quantum key distribution systems, basically, as I explained, I'm trying to correlate the explanations I've given in the quantum mechanics. It's basically an inherit of whatever property it has, quantum channel, and trying to build a QKD system, quantum key distribution systems. So these systems has two channels. One is a quantum channel where used for transmission of photons. The quantum channel used to transmission of photons or qubits. And classical channel is like a upper layer of quantum channel, which facilitates quantum things to happen, and it used for post processing, because a quantum channel is a one way and you cannot do it in a two ways, and it's very as it has a loss, all that. So classical channel also needs to be assisted with quantum channel in order to produce keys. But other thing is the classical channel can be open. if someone try to tap this classical channel, he may not be able to get or track the key. That is already proven security, which delivers by EQK systems. And how to obtain a key? So there are two mechanisms to obtain a key. One is a set of non-orthogonal quantum states, or basically these are single photons, qubit by qubit. Single photon is used to transmit a bit of information from one end to another end. And other mechanism is entanglement of photons. Entangled photons is nothing but relating two or more photons and according to some relations. That's where you learned yesterday's a Bell state, where two photons were interconnected, or it's a linear combination of two photons. When you observe behavior of one photon, you come to know that behavior of another photon. It's basically a pair of shoes where one shoe is one pack, another shoe is another back, right? Left hand shoe is one pack and right hand shoe. It's completely sealed. Just to jumble it and keep one shoe, one box here and send one box to US, right? So if you measure, you just open a box and see what shoe is, what type is left or right, then you come to know that what is another end. It's basically a pair. If you identify one out of it, you might be knowing another. But in quantum, these pairs, it changes its behavior frequently, right? So if one becomes left, another becomes right, another becomes left and right. This switching or state change happen in less than a nanosecond time. So it is very hard to attacker to predict these kind of switching, but once you measure, then it's collapsed, right? So this behavior, entanglement behaviors, are used to transfer the information from one end to other end. So these are two mechanisms where all the key distribution, quantum key distribution problems are used. One is a single photon technology, where non-orthogonal quantum states are prepared and sent it to receiver to get. Another one is entanglement based things, where two photons were entangled together and then keep one copy, another copy to send and to measure it. Right? So these are two mechanisms to obtain key. And as I explained, if some man in the middle attack or intruder in the quantum channel, it introduces traces. So it makes a detectable errors. So if you have error threshold, if it goes beyond that error threshold, you can identify this. So two important principles I have already explained. One is a no cloning theorem, and uncertainty principles are used so that any Eve cannot copy the quantum state sent by center. That's the no cloning theorem. And uncertainty, you cannot measure both the bases simultaneously. So these are like two important properties which conceals a complete quantum safe system. Right. Okay, so there are some process. I hope you familiar with. If someone is going through this QKD process, it's a familiar. It starts from center and receiver, a basic computer, because all the quantum channels, if you see quantum devices, which is operated by a classical computer. So this is basically lasers and detectors kind of stuff. It has a layer of optical layer, and it has a electronics layer, and it's a computing layer. That's a CPU level. So all the optical materials are operated by a computer. So as I said, it needs a classical channel as well as a quantum channel in order to establish a key. So initially it starts with some classical authentication systems, and then it goes for a quantum exchange of data, where it exchanges some bits from one end to other end, and then starts some shifting. And this shifting is basically another important property of photon is this: the photon travels from one end to another end It is not a direct path. It takes from a straight path from one end to other end. It may take any different paths. So it is not a direct path. It may take a zigzag left or zigzag right. So it doesn't guarantee that a sender sends a photon 1, it receives first, photon 2 second, and in that order. It may take the photon 1 may take any route and may reaches as a 10th photon in that other end. Another important thing, it may lose somewhere. It may not reach to receiver end. So there are huge loss, and it unpredictable behavior. It is very difficult to derive the key straightforward. So we need to follow some steps to derive the key, right? So these are the steps. Once the photon occurrence event happen, then you need to perform this sequence of steps, starting from shifting and error correction and verification, privacy amplification, in order to obtain a secret key. Because of the nature of photons, it is not straightforward, just convert, encode and decoding happening. So these are like the important steps which needs to follow all type of QKD protocol, the quantum key distribution protocols, to arrive a key. Right. So the shifting, as I said, the photons order the receiver end may be differ with photon order in the center end. So they need to agree on some basis choice selection and how to negotiate that. And once it is shifted, then there are errors may be possible. Errors, the chances of error is, anyway, receiver is using different bases. If you remember in the last slide, I explained choice of basis is independent for receiver. So you can use any basis. It reveals the if he use a wrong basis choice, then it makes introduce error. That error needs to be correct between these two keys without exchanging any information of keys. So that is happening with the encoder and decoder. Basically, this LDPC is a low density parity check error code. There are many error coding techniques. I just this is an simple example to understand it. Right? So error correction happen, and then make sure that both the end we have similar key, symmetric key. Some error verification process and privacy amplification. So privacy amplification is try to reduce the information leakages during this, because the only track we can know this information leakage during quantum channel we can identify, but other transaction, all business happening in the classical channel. So there is a chance that attacker can attack these and gain some information in these two channels, classical channels. So what we are trying to do here is just discard some bits in both the keys and or manipulate these keys in such a way that amplify the privacy of the keys so that it becomes ultra secure. Then you can use it for any applications. So if you look at the diagram here, it's a raw data detection, basically a photon detection events. And here you see this color, pink color, dark pink is leaked bits because it's already lost or leaked by someone. And then it is a shifted key. After that, size is reduced. We just change the alignment, and then keys used for parameter estimation. Parameter estimation is there any loss or is there any error due to the attacker may intrude? So those things, sort of parameters are computed, and then finally we get error corrected key and verified key, and remove some of the parts. We get the privacy amplified keys. So this key is used for authentication or other, and portion of this key is stored to make frequent communications like authentication for a next step. So this is a kind of things. If you look at the sizes we have got here, if I get a 1 million bits, we may get 1/10 of one single bit. So the amount of loss during this post processing also is huge. So if you look at 1 KB, then you maybe end up with 2-3 bits. So huge loss is encountering in the quantum process, quantum channel, as well as the classical channel during this process, right? So quantum key distribution classifications. So we have classification like discrete variable and continuous variable. So this is basically after measuring that photons, there are two classification outcome can be two variables. One is a discrete variable, another one is a continuous variable. So discrete variable I explained earlier is just single photons, countable single photons. Continuous variable, it's basically a signals. It is a quadrature of signals and it has a phase and modulation. It looks at continuous variables, right? So under this discrete category, we have two different protocol bases. One is a prepare and measure protocol, and another one is the entanglement based protocol. So prepare and measure protocol is designed in such a way that prepare the qubits and send it to receiver, and receiver measure it. Straightforward. So entanglement photon is randomly prepare entanglement things and send it to multiple users where they can measure. So I'm going to explain one by one in following slides. So under the prepare and measure, we have three categories. One is phase encoding, polarization, and time bin encoding. So these are like, there are many protocols available in literature every day, protocols coming in, but the base of this prepare and measure is BB84. Bennett and Prasad 84, they published this protocol, and IEEE, I think the conference happened in India. So first protocol in quantum is published and accepted by IAC in one of the conference, IEEE conference. And followed by, there are many variations of BB84, and these setups are basically what kind of equipments, quantum equipments you are using, and what kind of experimental set. But overall, the goal is prepare the photons and send it to others. So it's all, since it's all time driven and losses, experimentals are trying to improve their systems. So that's where all the protocols is. Basically, a protocol is what? It's a set of procedures. When you change the procedures, you may get some improvement. Similarly, entanglement based, it has a device independent and semi-device independent. And on continuous variable, we have discrete and Gaussian modulation. It's all, since it's a derives continuous function, it has two modulations, discrete and Gaussian. According to quantum channel classification, facilitation of channels, one is you can use a wired channel, which is optical fiber, and you can use wireless medium free space. Okay, so types of QKD, discrete and continuous, as I said, different parameters. For example, it starts from key encoding, it uses photon polarization. So polarization is nothing but, so you have to create a single photon and make it polarized like spin, and then measure the time of arrival of photon. Photon order is measured by time of arrival. Here in continuous case, it is like a field of energy, electromagnetic energy, which is looks a wave, and then the wave can be measured with these quadratures. Based on that measure, we take encode and decode the bits. And detections. So here its direction is measured. Here is a single photon. You can use the detectors to catch or not catch, click or no click. But here is a coherent case. So we use kind of technology called homodyne and heterodyne. So the homodyne technologies consumes the optical pulses and produces the equal electrical pulses, and with that electric pulse, it produces the analog to digital converters. Right. So, and post processing, as I said in the previous QKD process, we need to do once post processing once this quantum business is done. After computing the qubit transactions, you have to do a certain classical level post processing in your computer, or if you use some special electronics kind of FPGAs, you have to do more post processing. Then security, both are delivering the same security because both operates on the same physics underlying principles, but there are some advantages and disadvantages in both the protocols. And classification wise, discrete variable QKDs, BB84 and decoy state, there are so many protocols coming in. And CV QKD, there is one way and two ways possible in CV. And here is basically Gaussian, and since it follows some distributions, we try to use some Gaussian model to measure these things. Okay, let's quickly go through what is a discrete variable QKDs. So discrete variable QKDs under, I'm going to discuss two things. One is prepare and measure, and another one is entanglement based. Ma'am, may I know how much time left?
Sir, we can continue till 11:45.
11:45. So hardly I have 45 minutes. Right?
Okay, yes, sir. Yes, sir.
Thank you. Prepare and measure protocols. So prepare and measure, as I said, prepare a qubit and then encode the information in it and send it to a receiver. A receiver receive it with some measurement equipment that I have explained, the basis choice, and get the results. Right. So it is basically a photon encoding and decoding mechanisms. So if you look at the diagram here, it simple and explains neatly how this channel operates. Center has a classical bit and converts to a qubit, this quantum bits, and send it to a quantum channel. And we have a classical channel where you can exchange this basis choice. Only basis choice. With this basis choice, the adversary may not know what bit corresponds to it. Okay. Now we're trying to compare the basis choice made by a center and basis choice made by a receiver. So he prepared a photon in the basis of BZ. It's a 0, directed 0, and he used the same basis BZ, and then we received the similar bits. See, and then he prepares the same, get 0 and use the same, but he applied BX, different basis choice. Then the bit becomes 1. Now it's a discrepancy. So likewise, you can prepare all 4 states of qubits and apply different basis choices, and receiver is open to have any basis choice. But according to principle, yesterday you might have heard, in principle 50% of the quantum times he should apply a similar basis choices according to quantum principles, right? So in that sense, without exchanging the qubit information or that, only with the basis choice, center and receiver can arrive at key after some post-processing protocols, right? And this is encoding decoding. In 1970, Stephen Welsner proposed a equivalence table, how this should look. Basically, a basis choice is get 0 and 1 is a one set, and diagonal so the plus minus is another set, where superposition of these two is mentioned in this get 0 and 1. Okay. So it has an encoding table. Straightforward, you can apply this encoding table and write your code on top of it, how to do encoding of qubits and decoding another end. So this is a simple measurement protocol, but it is not as simple as that when you realize in experiments, because this side you need a laser which needs to produce a single photon level, and you need to timestamp that photon, send it to a quantum channel. Receiver end, you have something called detector, which captures, it's like a photoelectric material. It runs on avalanche effect. Once the photon light energy hits, it produces a signal, optical signal, and then it goes to a electrical, convert to electrical pulses, and then electric pulse goes to a processing engine and time tags it, the time it receives. Everything is happening in the nanoseconds. It's basically one photon, one bin of photon is 1 nanosecond interval they used to send. So it's typically a complex systems because it's involving all hardware, since we're dealing with everything in a physical world, but it's a very secure channel. So under this prepare and measure, we have going to highlight some of the protocols. One is a BB84. It's a famous protocol. Everybody knows it. Bennett Prasad and Gil Prasad, and both proposed in 1984. This protocol exactly the same, prepares and uses the 4 basis choices and make the measurement. Another interesting protocol is a COW protocol, one-way coherent one-way protocol. Majorly in India also there are many experimental setups starting from IIT Madras and other PRL Ahmedabad RRI having this experimental setup for up to 100 kilometers. So this coherent one-way is improved version of BB84, where the coherent weak of pulses, continuous lasers being used. It works on the phase modulation concept, just changes the phases of basis choice. It's famous called a COW protocol. Other one is a B92. The Gil Prasad again proposed an improved version of BB84, where here is 4 types of measurement being used. BB84. Here only 2 types of measurements in B92, and make it a simplified version. Most of the commercial QKD systems are using B92 protocol. For further reading, you may be refer sites. It's publicly available. So other varieties are entanglement-based protocol. Entanglement, as explained, it's a linear correlation of 2 photons. It's called Einstein-Polsky quotient EPR. It's another way is called a Bell states. So here measurement is an important thing, but there is no center receiver concept. There is a common source which keep on producing the photons, right, in different forms. Receiver or center, Alice and Bob, any 2 users can apply basis choice of their own and then make bit. If they use the same basis choice, then they can get similar bit keys. If you use the different basis choice, they get the key differs. Right? In between any intruder, then this error rate will increase. Then we know any in between there is intruder, right? So based on this choice, they will run set of some classical protocols in order to arrive at common key. So this is an entanglement-based protocol. It also has some kind of a setup where you need detectors from both the end and to capture that, and time takers which time tags the photon arrival time and make these choices. And another important thing here is it operates on different wavelengths, because this, as I said, it's a light. It operates on 1550 nanometer wavelengths, but this is like you can use multi-parties. You can put here David and 4 users can become a network. So recently there is a 8 user network conducted by University of Bristol. Our Indian scientist, his name is Dr. Siddharth Joshi. He demonstrated 8 users can connect with a single source. Because if you look at the these type of prepare and measure protocols, only 2 parties can generate a key. It is a 2-party protocol and point to point. Here where you can make multi-parties even. So different wavelengths, you can spend it to multiple parties can generate a key at a time. So here if you see 2 protocols, E91, AICTE is a student of Natarajan Prasad. Here he proposed E91 entanglement based protocols. These protocols run on the basis choice, how to make a similar basis choice in a particular time. And BBM92, Bennett and Prasad and Mervin, it's an improved version of B91, where they try to improve the source and detectors, the pulse with sizes, and make more data rates. And continuous variable QKD systems. So continuous variable QKD systems, as I said, it is measurement outcome is a continuous signal where you cannot take a decision on the single yes or no type, or click or not, photon occurs or not, because it produces a continuous signal which has the amplitude and phase, because every waves it has a property of amplitude and phase modulations. With that, you can encode the informations in any one of the modulations. So for example, in this figure, you see it lies on these two quadratures, this information lies on these two quadratures. You can encode zeros and bits according to the quadratures that you prepare and send it to as a distribution to a receiver. Receiver applies the homodyne informatic directions, and then he captures which quadratures the signal occurs. Based on that, it decodes. So it's basically dealing with continuous functions from one end and measurement outcome. So it's basically a local oscilloscope and signal. This is a continuous signal is going to a 50-50 beam splitter. It's basically whatever comes in this light, it just fits to 50-50. And here is oscillator, it just oscillates your signal and send it to. So chances going to this route or this route is 50-50, 1/2. It's like a kind of tossing a coin. Basically, a continuous signal can go any one of the route. Based on that, they will encode. If it comes to this detector, it makes a 0. Come to this one, come to 1. 1. So likewise, you can encode and decode the information based according to the phase and modulations, amplitude modulations. So here these continuous variable QKD systems are proved that it can go for a long range QKD systems, but very few research are going on these areas. So protocol overview, coherent state protocol is new already proposed in this, and no switching protocol. So it operates in one similar basis for 100 qubits, and then it changes. So there is no switching happen between random choices between the zeros and ones. It says keep on sending one signal and then changes. So no, and squeezed state protocol is another important thing where the signals width is squeezed, so that in order to achieve for a long distances. So here, if you look at how this amplitude, the signal is qualified based on the phase fluctuation and the amplitude. So current state of the art, yes, Japan is already has a long distance QKD systems, and Spain is having a long range QKD system. Cambridge and Canada and China has demonstrated a long distance QKD systems. These are already available long distance. When I say a long distance, it's all 100 plus, but I'm not sure how. I did not put here how long it's, but it's all 100 plus. I worked in this quantum Cambridge network. It is 146 kilometer. It starts from the I think British Telecom in York University, and then it comes to Bristol. It's almost 146 kilometer. So what I'm saying is there's already demonstrations are happening in the long range QKD systems, and India also is supporting for quantum related things. I think you might be aware of. So here is since we are using classical channel or quantum channel, there is a SD and software defined network is very important to handle this quantum channel and classical channels. So there are different layers in application level. One is the application layer where the key is used, and key supplying layer, key management layer, and quantum layer. So quantum layer is basically a dark fiber which bundle with all the nodes. Then it can connect to a quantum key management layer where we can store the keys and generated keys, and that can be used for application layers. So this is a fundamental architecture for all the across all the thing, and this is being managed by the SDN controllers nowadays. And so as well as the network configuration, because this is a chaos quantum system, there is no network being deployed. At least quantum system is concerned, you have to connect with your general purpose computer and networking switches in order to make the IP enabled. Now there are some improved systems where you can dynamically configure IP and make it as a full network systems. But so far it is operation wise, there are some things still in operation. In Geneva, I think I missed another one. There was another one is in Geneva. It's supplied by ID Quantic. It's up and running, and in Canada is running. So there are some things is operationalized, something is it's still under the research. So some of the commercial systems are just for your reference. If you want to do experiments, you can use the ready-made package commercial systems. ID Quantic is providing, and Magic IQ and Toshiba all are almost it's fiber-based commercial systems are available. And you see there are some partners and investors been publishing some white papers using these systems, how to build a secure network. So coming to a free space, because so far we discussed in wired QKD systems. So free space, we have ISRO has demonstrated free space up to 3 in their buildings at almost 300 meters. I think it used laser based QKD systems where they successfully delivered the keys in collaboration with RRI Bangalore. And China, launched a satellite which is a quantum enabled satellite which is capable of generating keys more than 2,500 kilometers over wired as well as wireless QKDs. For further reference, you can refer this Chinese. It's a first satellite launch, and there are some follow-up satellites being planned by European and other countries as well. So another important thing is miniaturized devices. So other free space systems are bulky optics, and people trying to use on low cost and miniaturized devices, where Bristol and Oxford University published a work which is in Nature, where they're trying to produce some handheld QKD systems, where it's like a mobile phone, just pass the laser and generate the keys, handheld kind of stuff. So beyond QKD, I think this quantum randomness is another important property. It's already been discussed by Dr. Prem, where it is a physical way, a nature way of producing qubits. As I mentioned, the qubit is a nature source. So there is no one can influence in that. So it delivers a nature quantum true random sources. And another area of research is quantum coin flipping, where it used for a bit commitment protocols, where sender and receiver is no longer trust each other. They are in a blockchain environment. Say we are trying to do some trading or that, so we no need to trust each other. You can write, you can try this bit commitment protocol initially to get some commitment. So try to commit some thing and verify both are mutually authenticated. So for those things, you can use this bit commitment protocols. Quantum money, as I explained earlier, you can use this quantum money concept for generating tokens. So that tokens as a private tokens, quantum, it's basically a qubit. You can generate qubit and embed with some of the chip things, and chips can be given to a user. You can store that quantum states in your bank to verify. So since these quantum states are prone to change, if someone is modifying, you may get verified. So this quantum money concept is used like generating tokens in different purposes, digital tokens. And quantum fingerprinting is another interesting area to do a research, where you can verify and swap the quantum states. So this fingerprinting used in hardware devices like our OS and other, sorry, less than the hardware devices, you can make these fingerprints, verify it whether your OS or your firmwares are genuine or your applications are genuine. And quantum public key cryptosystem also coming. It's basically a one-way function, trapdoor one-way function. It is under research. If it's a theoretical research, not much is done in this area. And quantum digital signatures already been explained, I think, by Dr. Prem, where generator signer verification. Generator basically generates the qubits and then signs the qubits using dedicated signing mechanism. Only the verification use measurement devices can verify, user can verify in publicly, right? And there is a semi-quantum approach where one side the state qubits can be prepared by the quantum machines and verified by the classical machines. That is called a semi-quantum digital signatures also. So another futuristic research areas. Okay, so some of the interesting examples that we here would like to see is it has an examples of banking sectors, whatever security cost centers this quantum is using. Banking already, couple of banks in Europe has been implemented. Their data centers are empowered with these QKD systems and QKD networks. And the quantum in mobile phone level is the research are started already. SK Telecom and ID Quantic Switzerland both is demonstrated quantum random number in their mobile phones, right? So where the random numbers can be used for as a OTP, or it can be used as a password generator, so many things. So it is realized in a chip level and can be implemented with your mobile phones. And randomness has a huge market where randomness used in simulations, gaming, lottery, and so on. So it has different applications since it's true random numbers. And automatic security is autonomous and connected cars where you can embed the quantum chips over there to generate secret keys and token and verify that. So because all nowadays autonomous cars need to be secure, or autonomous vehicles, so where people are trying to explore what are different. Typical cryptography is there are many applications as we discussed in the key distribution space, digital signatures, and so on. And telecom, whatever the communications that needs to be in telecom. So telecom has a huge applications in this one. An IoT device, as we said, most of the devices like medical devices or payment devices or IoT devices where there are many applications. So just to create an interest, I've grabbed this from Damayanti, one of her conference. She presented this. This is like interesting example. So where the bank is having a quantum machines where they can prepare a qubits and then store it in some chip like this and then give it to a client. So this is basically a quantum enabled chip. You can store some qubits in some form, right? So whenever the client uses this card, where instead of finding other signals, you just read these qubits in the payment card reader and then verify with the bank server. So this can be easily verified, the true quantum, the states which is prepared by the original states prepared by the bank and the states which in the card, then mutually authenticate. So if someone tried to change the states, because this is a classical version of a quantum state. If you change this classical version, so nothing will affect in the quantum, but the quantum device will know there is a change in this order. So these type of simple applications already been the quantum is used, and beyond that, people used for a data center for a bulk network encryptions. So where banks is having a lot of data centers where this QKD is used heavily to do a bulk encryption kind of stocks. And other interesting example nowadays is wireless QKD systems. People are trying to build uh, the contactless payment cards using this quantum random number generator and quantum key distribution systems. So these are pretty much about the application space, and it's coming to reality nowadays because all the communication equipments are now available in market. So people started experimenting it in their. So it has some current practical challenges which explores our researchers. One is these equipments are sensitive, optical equipments, and high cost. It's really expensive to do research, and companies or industries are a little bit hesitate to adapt this kind of infrastructure. And these devices are not mature enough because it's these growing research, and devices are mature enough to precisely measure and prepare the quantum informations and send it to user. And lack of network encryptions. So when you go for a long range QKD systems, it is incompatible with integrate with the conventional architecture because it needs a dedicated fiber channel, and it operating frequency is different, and it has a huge loss, and it is vulnerable to the external lightings, heat, so on. So it is incompatible with integrating with existing node. It is not a straightforward. And limitations, as I said, the losses. So for a 1 kilometer, it causes 10 dB of loss. It's a heavy loss, and the stability is not that great from it. So huge loss and noise influences. The photons are prone to influence of external factors. So it produces more noises. So that's a great challenge where researchers are working on how to overcome these losses. So that's where they proposed free space systems where you can reduce noise. Still, the free space systems are will not work on the ambient light or in a normal daylight. So you have to conduct experiments in the night time in a dark light so that you can reduce the significant noises. And standard wise and certification wise, still it to be standardized. Implementation and experimental setup needs to be standardized, and certification needs to be done. And it is on the transit from the laboratory, research laboratory to commercialization. Okay, let's conclude, at least to summarize what is to be we have discussed so far and what is a future perspectives. So as I said, these principles provides unconditional security in theory, but still there are some gaps in practice. No, but it's a guarantee that we can produce quantum safe communication infrastructure. But the challenges is like due to imperfect devices, distance and losses and so on. And it's expensive. More than that, it is expensive it's like a kind of a cost center solution. And commercialization of QKD's quantum technologies slowly is going on, and all countries started a mission, quantum mission, because it's a big business, not only a computing and everywhere. It's a big missions where government is investing heavily, and private also. Computing industry like Google, IBM, Amazon, everybody started in the quantum computing industry. And still a lot more to explore in this area. And quantum is only not a solution where people are trying to combine with post-quantum solutions, wherein make a hybrid systems that can be served very well to current existing threats like ransomware and other kind of attacks. How we can protect using this quantum and post-quantum. And skill set is concerned in India, I think everybody knows that we not have much workforce to work on this kind of cutting edge technology, and slowly government is sourcing fund to build a strong workforce and skill set in India. So that is pretty much futuristic, and hope it's very difficult to get the hardwares or equipments at this point of time. I believe most of you are computer scientists. Maybe you can try with experiencing these kind of a simulation tools to experience quantum cube. So this is basically San Andrews. It's a UK university. They provide simulation tools online. That's this simulation you may not generate data out of it, but you can visualize how these quantum qubits are prepared and send it to other end receive, and how this gives interference working. Right? And qkdsimulator.com is another. This is a project where you can download some of the data points. You can set the photons, number of photons that need to be sent, number of received photons, and error rate, everything, and then you can download some data for your analysis. And qnetsim.info, where it direct to GitHub, where you can download a code that's a Python and C++. There are many varieties of code you can download and install, where you can generate. And there is some Python packages, qkdsim. That qkdsim is developed by Vienna, University of Vienna, where you can download and use it. It's a Python code. You can use it for different protocol implementations. Even RRI, Raman Research Institute, Bengaluru, is a similar simulator where you can. That is not publicly available, but still you can make a request and use those things. These are like if you are working in the application level or protocol level, this will help you to design new protocols and come up with the new ideas. But with this, I would like to thank you everybody, and these are some references, and this is my contact ID. You can contact me anything. I'm happy to take questions now.
Sir, I have a small doubt. Like if we have to combine like QKD and post-quantum cryptography together, like how is it possible, sir? What are the prospects of such a kind of ideas, sir? Like,
Yes.
are there any combination of post-quantum cryptography protocols? If we conjugate it with QKD like protocols, then we can create more secure systems, I guess. So, are there any prospects?
Hybrid QKD, where quantum key distribution system has certain handicaps. The one handicap is if you take out the data from the quantum channel, then it loses.
Yes, sir.
It is secure until it is in the quantum channel. If you take out the key for application layer, then it loses the properties. So in those cases, PQC, the post-quantum ideas, can help to deliver the last mile security. But in terms of a comparison, as I said, these both are different world.
Yes,
one
sir.
work on the logical world, another one work on the physical world. So there are some advantages and disadvantages. If you want to compare it in terms of security, yes, it proves unconditional security, but there is a post-quantum. It is still a conditional security under certain constraints, and post-quantum algorithms is works under certain assumptions, mathematical assumptions. It is very hard to realize in a practical scenario. Similarly, a quantum things, it also runs on, it's not in assumptions, but realizing the qubits in a real time is very, very hard. And using a proper equipments to handle these things, another challenging implementation challenges. In terms of cost comparison, yes, it is expensive now, and if you go with the post quantum, you no need to change any one of your infrastructure. Still, we can climb secure. there are many what do you call phenomena where you can make a comparison in terms of security or in terms of benefit wise or in terms of operation wise.
Okay, sir. Thank you, sir.
Any other
Thank you, sir.
participant?
Will the QKD use entanglement?
Sorry.
Entanglement. Will
Yeah.
QKD use entanglement, sir?
Will QKD use entanglement? Okay, so as I already explained, one type is there are two types. One is prepare and measure. Another one is entanglement.
Mhm.
You look at my presentation, it's there. So entanglement based on one idea where you can disperse key for various users. That's definitely it.
Yeah. Okay, sir. Thank you, sir.
Any other participants? So thank you very much, sir, for this wonderful presentation on all these topics, which gives us so much of knowledge in exploring various ideas in these domains, sir. So thanks a lot, sir.
Pleasure, ma'am. So I would like to thank you, Vidya, ma'am, Dr. Vidya, and head of the department and management at university. So I'm alumni, and so I'm feel proud of this type of crowds. Thank you very much. Look forward to work with you.